In this video, we will talk about equations of motion and constants of motion. An equation of motion for a system, or an EOM, is just a shorthand way of referring to an acceleration. That is, a second-order time derivative. For example, the equation of motion for a simple harmonic oscillator is this: x double dot equals minus omega squared x. As you can see, an equation of motion is usually a differential equation. If you need more than one generalized coordinate to describe a system, then for each one you have an equation of motion. So if you need the coordinates r and phi to describe a system, then you will have one equation of motion for r, which would be r double dot equals something, and another equation of motion for phi, which would be phi double dot equals something. In contrast, a constant of motion is a quantity that is conserved as the system evolves. It is usually an expression which is constructed out of the coordinates and the velocities. For example, the energy of a simple harmonic oscillator is a constant of its motion, assuming no external forces or friction and so on. And the expression that we can write for it is 1/2 m x dot squared plus 1/2 k x squared for the particular case of a mass on a spring. As I said, this is an expression in terms of the position and the velocities. How do we show that this quantity is a constant of motion? Interestingly, we can show it by using the equations of motion. What we do is we take the quantity that we claim is a constant of motion and take its time derivative. Where in the last line, we have used the fact that the equation of motion is x double dot equals minus omega squared x, plug that in for x double dot, and shown that this quantity is 0. Since the total time derivative of the quantity, notice that this is dE over dt, not partially over partial t. Since the total time derivative is 0, then that shows that this quantity is constant in the motion in spite of the implicit time dependencies uh, due to x dot and x double dot and x varying with time. In spite of all of them varying with time, they combine in such a way that the time derivative is 0, and so this quantity is a constant which doesn't change during the motion of the system, and so this is a constant of motion.